Welcome to Geometry, Lesson 6.4 and 6.5. This is going to be the last video for Chapter 6, and we're looking at rectangles, rhombi, squares, trapezoids, and kites. Here's the first list of theorems. This is for 6.4. Go ahead and record these theorems on your paper, and be sure to use the pictures that I'm going to present to help you define these theorems. So let's begin with theorem 6.4.1. The diagonals of a rectangle are congruent. So we have a figure, PQRS, and you can see that two diagonals are drawn and that they meet at point T. What this theorem is telling us is that PR is congruent to QS. So PR is congruent to QS. That means that they are the same length. Let's take a look at one of the homework problems. Homework problem number 1 says find each length in rectangle PQRS. It tells us that find QS if PR equals 12. Well, if they're congruent to each other, that will give us the information that they're equal to each other, and if PR is 12, then QS would be 12. Theorem 6.4.2. The diagonals of a rhombus bisects two opposite angles. So, if we take one of these, okay, we'll get this eventually. If we take one of these diagonals, this is FH, it bisects two opposite angles. So what they're talking about is the diagonal bisects angle F and angle H. If we use the other diagonal, EG, then EG bisects angle E and angle G. This creates a situation of quite a few congruent angles. So HEG, which is angle 6, is congruent to FEG because it's bisected. So these two angles would be congruent to each other. And HGE would be congruent to F. HGE would be congruent to FGE, and FGE is 60 degrees, so that means that HGE would be 60 degrees. And these opposite angles we've learned from rhombi are congruent to each other, so both of these angles would be 60 degrees. Times 2. With this other diagonal, we have a situation where we have EHF is congruent to GHF, and EFH is congruent to GFH. And both angle H and F are congruent to each other, so each one of these angles will be congruent. So where it says number 4, this is also a number 4, this is a number 4, and this is a number 4. So quite a few properties are completed by just the fact that this rhombus, the diagonal, bisects two opposite angles. Let's take a look at some homework. Homework number 7. It says, find the measure of each angle in rhombus EFGH. one of the things I'm going to do is go ahead and clear this so we can look at it. If the measure of angle FGH, so FGH is 2 times 60, which is 120. I'm sorry, find the measure of each angle in this rhombus. And it says A, the measure of FGH is 2 times 60, which is 120, which we already talked about. So 2 times 60, because they were bisected angles and they're congruent to each other. And that will be your answer. So 120 degrees for that answer. Theorem 6.4.3. The diagonals of a rhombus are perpendicular. So this helps you to solve if you're lacking angle measurements. You know that all 4 of these measurements are 90 degrees, and this creates 4 90 degrees triangles, which means that you can actually solve for sides with the properties of 90 degree triangles. And as an example, in triangle FIG, you have a 90 degree angle and a 60 degree angle. That makes this a special 90, 30, 60 right triangle. So if angle 5 is perpendicular to angle 1, and angle 5 is 90 degrees, angle 1 will be 90 degrees because they're vertical angles, and also because of the definition of the rhombus. Let's take a look at homework number 7. Find the measure of each angle in rhombus EFGH, and it says the measure of angle 5. Well, they already told you that these diagonals create perpendicular lines, which create 90 degree angles, so angle 5 is 90 degrees. Theorem 6.4.4, if the diagonals of a parallelogram are congruent, it is a rectangle. So in this rectangle, they show you the congruency marks. One of the things we know about rectangles is that AC, diagonal AC, is congruent to diagonal BD. These diagonals bisect each other, so AE is congruent to CE, and BE is congruent to DE. An example of how you would use this in a problem would be find the length of BD if CE was 5. So BD is the total diagonal. If CE is 5, CE is 1/2 of AC, which means that AC would be 10, and AC and BD are equal, so BD would equal 10. Theorem 6.4.5, if the diagonals of a parallelogram are perpendicular, then it's a rhombus. So this is actually a converse of one of our other theorems, and we're starting with the diagonals first. So if the diagonals are perpendicular, then it's a rhombus. It would be up to us to prove that they were perpendicular. And one of the things we know, first of all, is we have a 60 degree angle. In 6.4.3, its converse, we prove that angle 5 is congruent to angle 1, and that they're 90 degrees. So if they're 90 degrees, then that means that they have to be perpendicular to each other. Perpendicular angles are 90 degrees. So EG would be perpendicular to HF because they intersect and form right angles. Theorem 6.4.6. If one diagonal of a parallelogram bisects a pair of opposite angles, the parallelogram is a rhombus. So in this case, we have a diagonal. If we can prove that the opposite angles are congruent, then we know we have a rhombus. In Theorem 6.4.2, we proved that the diagonal of a rhombus bisects two opposite angles. So all we'd have to prove is that two of these angles are congruent, and we have met the requirement for 6.4.6. So if one diagonal, in this case it would be EG, bisects a pair of opposite angles, the parallelogram is a rhombus. Theorem 6.4.7. If two consecutive sides of a parallelogram are congruent, it is a rhombus. So in the last figure we talked about the angles. Now we just need to talk about the sides. So if we substitute the word parallelogram for quadrilateral in the definition of a rhombus, we now have our theorem. Looking at the figure to the right, we can see that there are four pairs of congruent consecutive sides. The sides are EH and HG, so we have EH and HG next to each other, and we have HG and GF next to each other, GF and FE next to each other, and FE and EH. And the last theorem for Chapter 6.4 is Theorem 6.4.8. Two parallel lines are everywhere equidistant. This is just kind of thrown in here. We've actually had this before as a postulate. Now we have the theorem for it. And there are so many parallel lines. Let's just say that we've already intuitively known that two parallel lines are everywhere equidistant. Probably would have been a good idea to make this a theorem at the beginning of parallelograms. So the definition of parallel lines is two lines on a plane that never meet. They are always the same distance apart. In other words, they are everywhere equidistant. So they never meet, they're always the same distance apart, and this works with our parallelograms. We know that if we have these two parallel lines, all we have to do is draw two more parallel lines, and guess what? We now have a parallelogram. So you might want to pause the video, make sure that you go back and have your pictures written down, because we're going to move on to lesson 6.5 theorems. So here they are, lesson 6.5 theorems, and there are 7 of them. Go ahead and write those down on your papers and get ready to draw some pictures. Theorem 6.5.1. The base angles of an isosceles trapezoid are congruent. When they talk about base angles, you have to remember that in a trapezoid, they're talking about these angles right here, but they are also talking about the angles on the other side of the trapezoid. So the trapezoid is a little different than our parallelograms. It only has one pair of parallel sides. K and J are parallel, H and I are parallel. If that's true, and KH is congruent to JI, which makes it an isosceles trapezoid, then angle H and angle I are congruent to each other, and angle K and angle J are congruent to each other. Theorem 6.5.2. This is the converse of 6.5.1. If a trapezoid has one pair of congruent base angles, it's isosceles. So if you're doing a proof and they actually tell you to find, to prove if a figure is a trapezoid, and they give you base angles first, then show that they're congruent, then you know that you're going to be referencing this theorem, theorem 6.5.2. If you are given a figure and told it's a trapezoid and that it's an isosceles trapezoid by proving that you have congruent sides, then you would use 6.5.1. 6.5.3, a trapezoid is isosceles if and only if its diagonals are congruent. So, here's another property. We know that we have these congruent sides. We know we have congruent angles. And we also know that the diagonals are congruent. Now, the diagonals of an isosceles trapezoid do not bisect each other. So what you will have is congruent segments here, and then you'll have congruent segments right here. And in the proofs, you would be proving using vertical angles, angle side angle, to prove individual triangles to show that its diagonals are congruent. Let's take a look at example 2 in your book. We have a trapezoid. We can see it has diagonals. We will have one angle measure. Everything else we have to prove. So it says find each measure in isosceles trapezoid. So now they've told us it's an isosceles trapezoid. So now we can go ahead and mark our congruency marks. And says the measure of angle ABC is 125 degrees. So that's for this angle, the total angle right here. Okay. AC, this diagonal AC, equals 7x. So AC is 7x. And BD, the other diagonal, is 4x plus 12. Now, what do we know about these isosceles trapezoids? Well, those diagonals are congruent. We just learned 3 properties in the last 3 theorems. So, we're going to find the measure of angle BAD. Well, these 2 angles right here are congruent. So BAD would be 125. That is because base angles of an isosceles trapezoid are congruent. Then it asks us to find the measure of ADC. ADC, well, we know that parallel lines imply basically that we're going to have these supplementary consecutive angles. So if A is 125, that would mean the total of angle D would be 180 minus 125, which is 55. Angle C, the measure of angle ABD. So ABD, that's the little one right here. And let me get a different color, and I'll color that in. So we're looking at ABD. Now ABD is this small triangle. We know that the whole angle is 125. ABD is congruent to BDC. How do we know that? Well, these are parallel lines. They're alternate interior angles. So BDC would be 30 degrees. Okay, E, the measure of angle AED. That's this angle right here. And this angle, AED, is an exterior angle to these two remote interior angles. We know that both of these were 30 degrees, so 30 plus 30 is 60 degrees. So F, we're going to find the measure of diagonal AC. And one of the things we already know about AC is that it is 7x. And we have its congruent diagonal, which is 4x plus 12. So we need to solve for the variable and then substitute to get our total measure. So 7x equals 4x plus 12. 3x equals 12. X equals 4. Let's replace the 4 for the 7x. AC equals 7 times 4, which is 28. And there we go. Those are just some of the applications we can do with a trapezoid, knowing the properties that we've just learned. Moving on to the next theorem, Theorem 6.5.4. The mid-segment of a trapezoid is parallel to the bases, and its length is the average of the lengths of the bases. So we have a figure. We have a trapezoid. This is not isosceles, by the way, this trapezoid. The mid-segment, MN, is parallel to AB and DC. So when you think about this figure, I want you to think about transversals. A lot of the transversal properties will be used to solve aspects of this figure. The length of MN is also the average of the length of the bases. So that creates a formula. If we call MN I, they set a formula here. The measure of I equals base 1 plus base 2 divided by 2. And let's look at an example. So this is example 3 in your book. You have a trapezoid, and this trapezoid has a mid-segment right here, MN. So let's go ahead and use the formula from the last slide and substitute the values that we have here. So MN, which is the mid-segment, equals PQ plus SR divided by 2. Now you may have noticed already that they, in the formula, used the larger segment of the trapezoid, the larger base, and then they add it to the smaller base. It doesn't matter. That's just a way to make the formula line up the same for everybody. If you add the smaller base first, that's fine. So find PQ and SR. If PQ equals 4R plus 2, and SR equals 2R, and MN equals 10 centimeters. So now you would take this formula, and you would substitute the values. So they flipped the formula here. And MN, right, MN is 10. Try that another way. MN is 10. So here it is, substitute in the formula. And we are going to find PQ, which is 4R plus 2, and there it is in the formula. And we're going to add it to 2R, and then we're going to divide it by 2. So 4R plus 2R is 6R. We have 2 left over plus 2. And if you multiply both sides by 2 to undo this divisor, you will now have 20 on your other side. 6r equals 18. 18 divided by 6 is 3. So r equals 3, and let's substitute the 3 into our base lengths. So PQ equals 4 times 3 plus 2, which equals 14 centimeters, and SR equals 2 times 3, which equals 6 centimeters. And that's how you would go ahead and solve for this mid segment, or solve for the bases. In this example, we solved for bases. They could have also have asked you, given you information on the bases, and asked you to solve for the mid segment. You would simply substitute the known values into that formula. Theorem 6.5.5. Exactly one pair of opposite angles in a kite are congruent. We've talked in class about what a kite is, and basically a kite has one set of consecutive congruent sides and then another set with a different length of consecutive congruent sides. If you draw a diagonal, you create two triangles that are congruent to each other. And that's because of side, 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 and they're using the reflexive property to state that WY is congruent to YW. So that means that triangle WXY is congruent to triangle XWY because of side, side, side. And that means that angle X is congruent to angle Z by CPCTC. Now in a kite, if the second set of opposite angles, which are angle W and angle Y, were congruent, then the figure would actually be a parallelogram. For this to be a kite, W would have to not be congruent to Y. Okay? So you'll have one set of angles that are congruent, X and Z, but you will not have a second set are congruent. Y and W are not congruent to each other. Theorem 6.5.6. The diagonals of a kite are perpendicular. So diagonal IE and diagonal KT meet and form four 90-degree angles. So we've got angle KXE, angle TXE, angle KX, this should say, sorry, on here, KXI, and angle TXI, all equal 90 degrees. We also know that these two angles, angle K and angle T are congruent to each other, but angle I and angle E are not congruent to each other. Theorem 6.5.7. The axis of symmetry bisects the crossbar in the two non-congruent angles of a kite. Okay. The axis of symmetry is a line that is drawn in a figure to cut it exactly in half so that both sides reflect each other. And we'll be learning about symmetry later on in your book. This axis of symmetry, by its properties, will bisect the crossbar. The crossbar is KT. And the two non-congruent angles of a kite. So it will also bisect angle I and angle E. So it will now make a situation where we have, let me get a different color, KX and xt will be congruent. And angle KEI and angle, KEI and angle TEI will be congruent to each other. So the axis of symmetry, IE, bisects the crossbar KT, and the new two non-congruent angles, which were I and E, are also bisected by this axis of symmetry. So that means also, by the way, that these two angles will be congruent to each other. They will not be congruent to these angles on the bottom, but they will be congruent to each other. Let's take a look at example 4, and this is where we put all of these properties together. Find each measure in kite KITE if the measure of XKE, so XKE is 55, and KI is congruent to KE. So KI is less than KE. Okay. So the measure of angle KTE, that's this measure right here, will equal 55 because it is a congruent angle that was bisected by KT, this crossbar. And that's isosceles triangle theorem. You have, if you take a look, two congruent sides in this triangle, and we have two congruent base angles. The measure of TXE equals 90 degrees, and that's because the diagonals of a kite are perpendicular. The measure of angle KEX, that is new color right here, equals 90 minus 55. Oh, okay. Sorry, that threw me for a little bit of a loop. Your triangle is 180 degrees. From the beginning, we have subtracted whatever angles we have from our triangle to determine what the third angle would be. And we know 180 minus 90 will be 90. They just took that step for you. So they've already done that step, and 90 minus 55 equals 35 degrees. The measure of KET, that's this total angle, would be 2 times 35, which is 70. And it says 35 degrees is finding E, which is KIE. We don't have any lengths of the sides of these triangles. We don't have any variables to solve for, but one of the things we do know, because the measure of angle KIE right here, this angle, we can't determine this exactly. The greater angle theorem implies that its measure is greater than KEI. So KIE would be greater than KEI. And angle KIE must be acute, since acute is less than 90 degrees, since KXI is 90 degrees. Remember, if you have 180 and you take away 90, you only have 90 left over to split between these two angles. So we know that KIE has to be less than 90 degrees. So that's how we can state it. So here's the measure of KIE. It's less than 90 degrees, and we know it's more than 35 degrees. So that's a little complicated, something to think about. And that's it, though, for chapter 6.5. So here's your homework. This is 2 days, and guess what? I just realized that this homework slide is not the right slide. So you'll have to look at your lesson plan that I handed out to do this, and let me write this in case somebody wants to do use lesson plan. And we'll cross this out. If you have any difficulties, please be sure to contact me. Please don't leave your problems blank, and go ahead and make sure that your pictures for your theorems are all in order. This is a lot of information to try to retain. I realize that, so you can use your sheet with theorems on your test. And just be sure to understand the concepts when you look at the theorems. So make sure that your pictures have the right congruency marks so that you will understand what's going on. Have a blessed day, and I'll see you in class soon.